So line AB and line CD are parallel. This is a symbol, the double bars. But now look what I'm going to do now. I'm going to go ahead and do it with a different color marker here. I'm going to draw a line through AC going down and another line through BD going down. And I'm going to say that these two are parallel now, the two green lines. So I'm going to say that line AC is parallel. Look at the double bars. That's a symbol. AC, here's AC, the green one, is parallel to line BD. Notice the quadrilateral that's inside that four-sided figure. That is a parallelogram. When both pairs of opposite sides are parallel, you're dealing with a parallelogram inside. Okay. In other words, imagine the sides going on forever without intersecting. Okay? Next word. It's a theorem about parallelograms. So go ahead and fill in the blanks there. This is your first theorem. Remember, a theorem is a law that's always true. Well, here's a law about parallelograms. It's kind of presented in an if-then statement. If something, then something. And this is always true about parallelograms. If a quadrilateral is a parallelogram, then its opposite sides are congruent. This is always the case. No matter what kind of parallelogram is thrown at you, the opposite sides are congruent all the time. So notice that. Sides PQ is congruent to RS. In other words, whatever size PQ is, however long it is, it's the same as RS. And then the same thing for these two sides. So that's always a feature that's true about parallelograms. The opposite sides are congruent. No, not alone. So we'll call that theorem 6.2. Opposite sides congruent. Next one. Theorem 6.3. If a quadrilateral is a parallelogram, look at this is another feature of it. Then the opposite angles are congruent. Let's fill in the blanks there. So this is another truth about parallelograms. Not only are opposite sides congruent, opposite angles are congruent. So you have angle Q is congruent to angle S, and angle R is congruent to angle P. All the time. Take it to the bank, it's always true. There. Next one. So I'm already throwing two theorems at you. Here's a third one now. And they're all about parallelograms. There's all kinds of special things that happen with parallelograms. Opposite sides congruent, opposite angles congruent. Look at the next one. If a quadrilateral is a parallelogram, then its consecutive angles are supplementary. We know that word supplementary. We've seen that before with angle relationships. Consecutive angles are supplementary. That means angles right next to each other. So P and Q are 180. Q and R are 180. R and S are 180. And S and P. So consecutive means right next to each other. Consecutive. This is always true. All right. So far, so good. And last theorem. I think it's the last one here. Yeah. So theorem 6.5. If a quadrilateral is a parallelogram, then its diagonals bisect each other. Look at the diagonals that are drawn. And this goes for any parallelogram. To bisect means to chop right in half. If I bisect something, I chop it in half. So the diagonals of a parallelogram chop each other in half. See? So notice from here to here is the exact same distance from here to here. PM is the same distance as MR. That's why you have the little hash mark here. The exact same distance. The diagonals, these are called diagonals, they chop each other in half. And it goes for any parallelogram you ever come across. So that's 4 theorems already. So this would indicate that these two are congruent. In other words, from MS, it's the same distance from to MQ. So these little hash marks indicate congruence, or same size, they mean the same thing. So the diagonals chop each other in half. So this diagonal chopped this in half, so these two are congruent. And this diagonal chopped this in half, so these two are congruent. It's just a strange, mysterious feature of parallelograms. All the time it happens. Now, let's try an example here. There's the answers. Let's go to example 1. Let's use some of these terms. STUV is a parallelogram. Notice the way they name it. STUV is a parallelogram. Find the unknown length. Okay, so we're on example 1. Notice the arrows. Look at this arrow on segment SV and the arrow on segment TU. Those arrows indicate that these two sides are parallel. So go on. If you were to extend these two sides, they would go on forever. If I were to extend this side and extend this side, they would go on forever without touching. That's what the arrows mean. And the same thing for segments ST and VU. Look at the double arrows. These two sides are parallel. So we're dealing with a parallelogram by definition. Yes? So right now you want to know what TU is in, right? You're going right into question A, huh? So they want to know what is the measure of segment TU? How big is it? What do you guys think? So how big is TU? 12? Okay, so Ellen says it's 12. Ellen, can you give me an argument for why it's 12? How do you know they're congruent? What theorem are you referring to? Theorem 6.5, 6.10, 6.3, which theorem are you referring to? You're right. Can you give me specifics of what theorem you're referring to? 6.5. Very nice. Let's see. That would be bisecting each other. 2. Let's see. So I'm looking for the theorem that says opposite sides are congruent, and I think it is 6.2. Yep. So it's the first one. Look at theorem 6.2. This law. Remember, a theorem is a law. This law says if you're dealing with a parallelogram, then the opposite sides are congruent. Remember, congruent means same sides. So Ellen is absolutely right that TU is 12. So let's fill in the blanks here. So TU is equal to SV because opposite sides of a parallelogram are congruent. Look at they're using symbolism here. This means parallelogram, that little symbol. We already know that means congruent. So they're having you write out the reason. So we know that TU is equal to SV because exactly what Ellen said, theorem 6.2 says opposite sides of a parallelogram are congruent. So we know TU is 12, so let's do 12 for SV. Cool. So all this lesson is parallelograms will be thrown at you, and you got to know how to navigate with the theorems I throw at you. In other words, knowing the theorems, we can make conclusions about stuff. How about WT? Let's see. So WT, from here to here. 14, Ms. Castro, give me an argument. How do you know WT is 14? So from here to here is 14 also? And from here to here is 14? Okay. You're on the right track. Why can't we? You're right. WT is 14, but give me the right reason. What theorem? What theorem allows me to conclude that WT is 14? Go ahead, Castro. Ellen, I'm coming to you. She can't get it. What theorem allows me to say that WT is 14 is my question.
I'm not sure.
Theorem 6.5 tells us. Because look at theorem 6.5. It says, look, if you're dealing with a parallelogram, the diagonals bisect each other. This one. So bisect, if you don't know what bisect means, maybe off to the side you can write chop in half. Chop in half. It's a fancy word. So bisect means chop in half. So this theorem, this law says, look, this diagonal right here chops in half this diagonal. Look, that's why this is congruent to that, and vice versa. The diagonals chop each other in half. That's why you have one hash mark here and one hash mark here. They're congruent. Two hash marks here, two hash marks here. They're congruent. So Ms. Castro is absolutely right. WT has to be 14 because this diagonal is chopped in half by SU. So this and this got to be congruent. So let's fill in the blanks here. So WT equals WB. We'll fill that in. So WT is 14. Substitute 14 for W. WB rather. Pretty straightforward, I think. Nothing too high for movement. Just laws of geometry, and you apply them to shapes. That's all we're doing. All right. Let's try the next one. Example 2. So it's on the same page or flip the page. Let's go to example 2 now. So it says JKLM is a parallelogram. Find the measure of angle L. So we got a parallelogram. It's obvious because look at the arrows. These two sides are parallel. These two sides are parallel. We're dealing with a parallelogram. How the heck am I going to solve for angle L? That's the question. Angle L. So L is 180? Okay, so how did you conclude that these two add up to be 180? What theorem are you using? What theorem? 6.5, 6.10, 6. What? So what theorem out of the 4 I just showed you? 6.4. Let's look at theorem 6.4. Look at theorem 6.4. If a quadrilateral is a parallelogram, we got a parallelogram, then its consecutive angles are supplementary. Supplementary means 180. So Ellen is actually absolutely right. So if we know that angle M is 135, then we can just take 180 minus this, and we'll get this one. These are consecutive. These are consecutive. These are consecutive. These are consecutive. The theorem says consecutive angles are supplementary. So let's fill in the blanks. So look at the reasoning. They're kind of thinking out loud for you, step by step. Measure of angle L plus a measure of angle M equals 180. Why? Well, it's theorem 6.4. consecutive angles of a parallelogram are supplementary. Again, that's a symbol for parallelogram. What's the next step in the reasoning? There it is. Replace angle M with 135. 180 minus 135 is going to be 45. So measure angle L is 45 degrees.